The innovations made possible by neural networks continue to astound me. They, like machine learning in general, are gradually seeping into our everyday lives, even if we don't realize it. In this video, we'll be talking about the basics of neural networks. But before we continue, I would like you to give this video a like and subscribe to this channel. They can be incredibly convoluted, and it's often not clear how they make judgments. The design, as one might expect from the name, is based on something common to all of us, the human brain. When seen in isolation, neurons, the brain's fundamental building blocks, are actually quite simple. Electrical impulses move from one neuron to another across a synapse connecting two neurons. A synapse will fire, or transmit an electrical impulse to the next neuron if the strength of the electrical impulse meets a particular threshold. When solving a problem, human brains take in data, process it, and then produce a solution. Neural networks roughly replicate this process. They acquire this ability like we do through training on labeled datasets. Now, what are neutral networks? Neural networks are a class of pattern recognition algorithms that are inspired by the structure of the human brain. By using a form of machine perception, they classify and organize raw sensory data. All real-world data, including pictures, videos, texts, and time series, must be converted into the numerical, vector-based patterns they recognize. They also help us to identify and organize data. They add a layer of classification and grouping to the information you store and manage. They aid in classifying data when given a labeled dataset to train on, and they can help unlabeled group data based on similarities among the example inputs. You can conceive of deep neural networks as parts of broader machine learning systems that also make use of methods for reinforcement learning, classification, and regression. They can extract features that are supplied to these other algorithms. Components of neural network. Input layer. The nodes from which the model receives data in order to make inferences and learn are called inputs. The data is transmitted to the hidden layer by the input nodes. Hidden layer. The input data undergoes all the computations in the hidden layer of neurons. A neural network may contain any number of hidden layers. A single hidden layer constitutes the smallest possible network. Output layer. The model's conclusions and outcomes are presented in the output layer. The output layer may contain a single node or several nodes. The output node is one for a binary classification problem, but in multi-class classification, the number of classes might be greater than one. Types of neural networks. Convolutional neural networks. Convolutional neural networks, CNN, have a first layer that is a three-dimensional arrangement of neurons rather than the traditional two-dimensional array. Only a fraction of the visual field is processed by each neuron in this layer. In this way, the network is able to comprehend the images piece by piece and do the necessary computations numerous times. Not surprisingly, CNNs excel at picture identification. Besides these examples, CNNs are also used for machine translation, computer vision, and speech recognition. Recurrent neural networks. Recurrent neural networks, RNN, were developed in the 1980s and make use of sequential data or time series data, which is particularly helpful for ordinal or temporal solutions in fields like language translation, NLP, speech recognition, and more. RNNs are also able to learn from training data, just like CNNs. One distinctive feature is that the output of one layer can be stored in memory and then sent back to neurons in a different layer. It's not only forward propagation, but rather more like a feedback network where information is processed again. Bidirectional recurrent neural networks, BRNN, gated recurrent units, GRUs, and long short-term memory, LSTM, are only a few examples of well-liked RN designs. Challenges of neural networks. Excess data needed. In order to perform successfully in production, neural networks often necessitate a large amount of training data and a number of parameters. You may adjust things like the number of hidden layers, the number of neurons in each layer, the rate at which you learn, the degree of regularization, and many other settings. To minimize the prediction error on some validation data and the prediction time, we must tweak the various parameters of neural networks. Time-consuming development. The development of neural networks is made very easy by the availability of numerous computer vision libraries. Developers needing finer-grained control over the algorithm's implementation may expect a much longer development time. A neural network is computationally expensive since it requires a processing time and a lot of data for training. Algorithms. The third reason for deep learning's rise in popularity is the development of better algorithms. Recent advances in algorithm development have largely resulted from making them operate considerably faster than previously, allowing for the usage of ever-increasing amounts of data. For more videos on deep learning and AI, give this video a like and subscribe to this channel. You can also watch our other videos popping on your screen right